Okay, and we are going to continue with timing circuits o circuitos de tiempo. And in timing circuits, now we have a case where we have to determine the method to solve for the capacitor's voltage VCT and the timing T, the time T, when a capacitor is initially charged. That's a very common problem or issue that we have to solve in this type of circuits, and the equations are different. So in the circuit we will see Vs is the voltage source, Vt negative is the negative going threshold voltage, Vt plus also the going threshold voltage, Vct is the final voltage the capacitor will reach. In this case is Vt plus. So let's see the circuit. This is the circuit and the equivalent circuit. At this moment is very important to determine the equations because we will use them a lot in timing circuits, and also you can apply these equations in any other similar circuit like the ones used for oscillators using op-amps. Okay, so so we have here a capacitor with a voltage source which I'm calling Vs. In some circuits we call it VDD if it is CMOS, or VCC if it is TTL. So you have here the switch which will be closed, and a resistor. Vi is the initial voltage that the capacitor has. So that initial voltage can be any value, 1 volt, 2 volts, 3 volts. This is the capacitor C and a current I of t. So this is the circuit in the t domain, in the time domain. Now to solve the circuit we will use the Laplace transform. So I'm converting the circuit into the transforming the circuit into the S domain, and right here you can see that in the S domain Vs has to be the Laplace transform for a constant is 1 over S. So this is Vs over S, this is a switch. Resistor R doesn't change with respect to time. The initial voltage Vi now is converted into Vi over S, and 1 over Cs is the equivalent in the Laplace transform. So to start solving this circuit we have the S domain, and notice right here, I'm going to center this circuit. Notice that we solve this by the two power supplies that we have, Vs minus Vi divided by S. That's equal to the drop voltages across R. So we have Is times R plus the drop voltage across 1 over Cs. So this is the equivalent of the voltages using KVL, we can say. So solving for Is, I pass this term to the other side and dividing. So it's Vs minus Vi divided by S over 1 Cs plus R. Now what is the capacitor voltage? The capacitor's voltage is the initial voltage plus I times 1 over Cs. And so I have Vi over S plus I substitute the Is which I got previously, and so the I over S is substituted, and you notice that now this one becomes a square because you are substituting this, and so S is squared, then you have C multiplying 1 over Cs plus R. So this C was in this area. Now we have here the Vi over S plus Vs minus Vi, and right here we do factorization, so we do the product S squared C over 1 over Cs. That's S, because S squared divided by S is S, and C over C is deleted. and then you multiply S squared C R, okay, or S squared RC. Okay, so this is where we are at this moment. So to continue solving that equation, we go to the right side, right here, and we get, right here, we get the equation continues. So we do the product, and then we multiply by 1 over RC, the top, numerator and denominator, and then applying partial fractions, we solve bi over s plus the new term a over s plus b over s plus 1 over RC. From here we solve for a, we solve for b, giving the limits s equal to 0 and the other one s equal to negative 1 RC. So we find a, this is the value, we find b, we substitute those values into this equation, the equation of the capacitor, and we notice that bi over s is repeated, but right here this is negative, this is positive, so they are deleted, and we only have bs over s plus this term, or minus this term. We apply inverse Laplace transform, and we have bs over 1 over s plus we have the constants outside the Laplace, and so this is the solution: bs minus bi times e to the negative t over RC for t greater than 0. From here we solve for t, and when we solve for t, we have RC ln of bs minus bi over bs minus bct. Okay. In your homework, you will do the steps that I was skipping here. How do you solve for t? Of course, I'm giving you the solution, but show me the steps. What are the steps that I follow to solve this? Entonces, su tarea es encontrar cuáles fueron los pasos para resolver aquí t. Okay. Now, this is the final equation, this formula, and notice that Bs is the power supply. This is the initial voltage of the capacitor. This is the power supply, and this is Bc of t. This is the capacitor's voltage. In other words, this is the new voltage you are willing to determine, but you have to determine this. For example, if the capacitor voltage is, the initial voltage is 1 volt, so you substitute, and Bs is 5 volts, so you say 5 minus 1, 5 minus, and you need to know how long will it take for the capacitor to reach Bc of t, so you can substitute it as, for example, 4 volts. So what is the time the capacitor will take to reach 4 volts when its initial voltage was 1 volt and the power supply was 5 volts? So you substitute it and you get the exact timing. Okay, and there are other circuits that we have to see, like monostables, but this will be in our next video in timing circuits. Thank you.